Okay, so in this video, we're going to take a look at testing for subspaces. All right, now, luckily, if we know that a set comes from a known vector space, then we don't need to go through the 10 properties. All right, so just remember, if we're given a set along with that definition of scalar addition, scalar multiplication and vector addition, right, then we would have to go through and look at these axioms here and make sure that all of them hold. All right, now the nice thing about subspaces is that if we're already working inside a known vector space, then the test whether the subset of a vector space is itself a vector space is a much shorter process. Right, so as it turns out, it comes down to three things. Right, so looking at our textbook here, okay, so this is theorem TSS in our textbook, and it states that suppose that V is a vector space and W is a subset of V. All right, so W is a subset of V, and we endow W with the same properties as V. So same addition, same scalar multiplication. Then W is a subspace if and only if three conditions are met. One, W is non-empty, so it contains at least a vector. Two, if X is an element of W and Y is an element of W, then X plus Y is in W. So it closed under scalar addition. Closed under vector addition. And three, if alpha is an element of C or the real numbers in our case, and X is an element of W, then alpha X is an element of W. So it's closed under scalar multiplication. Okay, so we just need to show these three different quantities. Okay, so now the first one, non-empty, usually we can just show that it contains the zero vector, right? That'll give us non-empty, right? We show that a vector is indeed in the subset. All right, and it's the other two and three that usually require some work. All right, now one thing to notice, to realize about this is an equivalence relation. What that means is this if and only if statement. So if one of these properties fails, then it is not a subspace. There is no need to check the other two. All right, all three must hold for the subset to be a subspace. Okay, all right, and notice the reason why we only need these three is here. Going back to board here, if we look at here our vector space axioms, the subset is already coming from a vector space. So if we notice the other axioms, commutativity, right, all these properties are inherited from the vector space that it is a subset of. So there's no need to reprove them, right? The only thing here is really the zero vector, but that's the one we'll choose to show that it's not empty. Right, but everything else just stems from properties of vector space, which these vectors are a subset of. All right, so let's take a look here at an example. Let's let W be the set where P is a polynomial. Right, element of P, a polynomial of degree 3 or less, such that P of 0 is equal to 0. Right, in other words, that 0 is a root. Right, so just to get an idea, right, here, right, this would be an example of a polynomial that has that property. So with this, right, both of these have a root 0, so right away we see, all right, it is not empty. Right, W is not an empty set. All right, and we can see it does in fact include the 0 vector. If I define here our 0 vector to be just the 0 function, right, then that also satisfies the condition that P of 0 is 0. All right, so now we want to check that it is the other two properties. So closed under vector addition. So we'll have two polynomials. All right, now one thing to notice that for any polynomial in W, it is going to be of this form. So there'll be no constant, right? And the reason for that is because 0 is a root, right? So when I plug in 0, the resulting polynomial should be 0. So the only way that happens is that there is no constant. All right, so I'll define P of 2 to be b1x plus b2x squared plus b3 x cubed. All right. Okay. And again, right, notice that, well, how do I know these are in W? Well, if you plug in 0 for x, you see that and evaluate it, you'll see that the results you get for both of them are 0. Okay, so it has 0 as a root. For both of these. So now what I want to do is, all right, let me see if it is closed under addition, right? These are just two general polynomials in W. What does okay. All right, and then we see here. Okay, so we'll define okay. All right, and again here, both of these we know that P of 0 is equal to 0, P2 of 0 is equal to 0. Okay, so when I add these two together, right, and I plug in 0, so A1 0 plus A2 times 0 plus A3 times 0. Okay. Plus B1 times 0 plus B2 times 0. So we get 0, the 0 polynomial, when I add P1, x and P2x. So what that tells me is it is in fact closed under scalar addition. Excuse me, vector addition. Okay, now let's take a look at alpha P1x. All right, so here we have alpha A1 A2x squared A3x cubed. All right, and we can see here that P alpha P1 of 0 is equal to alpha times 0, which is 0. So what we have is alpha P of x, P1 of x, is an element in W. All right, so it is closed under scalar multiplication. Okay. All right. So the set W defined in this way is indeed is a subspace of the polynomial space. All right, so that's how you would approach determining whether something is a subspace. Now, here's some examples where there are not subspaces. There are subsets, all right? So the first one is, let's take a look at the set W, which is the column vector in R2, such that 3x1 minus 5x2 is equal to 12. All right, so it's a line in the plane. Right, and right away we'd see it fails that it does not contain the 0 vector. Right, so here, 0 vector. So if we plug that into the restriction, the line in R2, all right, so we see that this is not true. So 0 is not an element of W, right? So W is not a subspace. All right, so again, only one of, we don't need to go move any further. If one of them fails, right, we can just move on to the next problem. Right now, let's look at another set. Let's say W is defined as x1, x2, x1 element of Z, x2 element of Z. So these are, again, Z is the set of integers. All right, now for this one, this one does have a 0 vector, right? Since 0 is an integer. But what we're going to see is that this does not hold for scalar multiplication, right? So let's say, for example, let's call some vector y to be 1, 1. Right? So here, this is an element of capital Y. But now let's take a look at this alpha times y, and let alpha equal to 1/2. So 1/2, 1, 1. So here I get 2 rational values, so that is not an element of W. So it is not closed under scalar multiplication. Okay, so that is how, again, just show that one of those properties does not hold, and then it is not a subspace. All right.